researcher at TD Ameritrade, as he mentioned. He's working on the exploration lab team, and he also advises PyData Ann Arbor and the AI Council at Ameritrade. And he's the core maintainer of Stumpy, which is one of the things he's going to tell us about today. Do you call it Stumpy or do you call it StemPy?
I won't hold it against you if you call it either. But personally, I call it Stumpy because Stumpy in itself is a word. So it makes it a lot easier, but I'm not going to get into the NumPy war.
Okay. That's probably wise to stay away from that one. So, but yeah, I hope you all join me in welcoming Sean and looking forward to learning about its applications.
Great. Let me share my screen real quick then.
Wait, but Brian, how do you pronounce it?
I mean, I already said Stumpy, and then he said Stumpy, so I'm clearly correct.
Cool. Can you guys see my screen? All right. So I'm super excited to be here today to be telling everybody about modern time series analysis with Stumpy. As Brian mentioned, my name is Sean Law. You can follow me on Twitter at SeanMyLaw. And if you'd like to follow the development of Stumpy, you can also follow the Stumpy_dev handle as well. Also, because I can't see the chat, I'm going to ask that if you have questions, please type it into the chat. And then whenever we see this raised hand, I'm going to hand it off to Brian to help me moderate. And first and foremost, I'd like to acknowledge some researchers. So researchers over at the University of California, Riverside. So that is Eamon Keogh's group, as well as at the University of New Mexico with Abdullah Mouin's group, both of these groups are really the inspiration behind what you're seeing in Stumpy. So I'm not in any way affiliated with these groups, although I do communicate with them to get sneak peeks of some of the upcoming research related to matrix profiles. Also, please realize that we're just at the tip of the iceberg. Everything that we're going to discuss here today there's really a lot of technical detail underneath the surface that I'll probably gloss over, but hopefully I'll provide enough intuition and motivation and hopefully help you establish some sort of understanding of how you might apply Stumpy to your everyday work. Also like to acknowledge Stitch Fix and the algorithms team, as well as a special shout out to Brian Bischoff, as well as Zach Winston for inviting me here and coordinating this talk. Also like to acknowledge TD Ameritrade, my employer, for not only allowing me to work on this project, but for giving me the time to come and share this with you. Just a quick note about me. So again, I'm Sean. I'm a senior applied research scientist and lead data scientist working on a team called the Exploration Lab at TD Ameritrade. So we're essentially a research and development team focused on exploring new and emerging technologies, or in the data science case, new and emerging methodologies that might help the company differentiate ourselves from our competitors. And Stumpy is one of these explorations that we found very, very useful, and we thought that we'd share it with the world. So what's the problem, right? We're talking about time series analysis, and we've sort of all been here, where somebody it's a business partner, maybe a collaborator that has some time series data. And they're breathing down your neck and they're saying, here's some time series data. Now perform some magic, Dr. McFancypants. And we've felt this many times before. And now if you're lucky, your data might contain only 10 data points. In this particular case, you see that data is trending upwards. It's not that hard. You can still visualize your data. But 10 data points isn't really that useful for most time series analysis cases. Now, what if your time series contained 100 data points? Now you're seeing sort of changes in your data moving up and down, right? Maybe you can compute some distributions from it. So still visualization is a great tool for this. Now you transition to about 1,000 data points. Now you might see something periodic, or there's some seasonality in your data. Now that's all fine and dandy, but once we get to about 10,000 data points, it becomes very, very hard to visualize and look for anything interesting. So if I were to draw your attention to this is not randomized data, this is a real data set. If I asked you, is there anything interesting about this data set? And I don't know about you, but if I look to the left and look to the right, I've already forgotten what I looked at last. And so, and what I will tell you is that we're gonna come back to this data set at the very end during our live demo, and then we'll explore this a little bit later on. But the point here is that anybody that gets a data set landing on their lap, hopefully you might feel just like me, this overwhelming sense of dread, right? Because really what you want to do is you want a way that will allow you to tell you where you should focus first on that data set. And oftentimes we just sort of wish that there was some magic spell that we can cast and just wish it all away, or at least point us in the right direction, right? Help us gain insights into that data set. Now, here are some common magic spells, so to speak. Visualization. So as we just showed before, we can visualize our data. But also, once we get to about 10,000 data points, or 1,000 data points for that matter, it becomes very, very hard, right? It doesn't become that useful anymore. Now we can reach for our good friend statistics and analyze properties from that time series, such as the mean, median, mode. You might look at other global statistics like the global max, the global min. But when we're analyzing time series data, very, very rarely are we interested in these global statistics. Because what we're more interested in is context, right? That is data points that are sequential. As a group of data points, are they interesting or are they uninteresting? Now, if you're lucky enough and know that there's some sort of conserved behavior inside your data set, you might build an ARIMA model, an autoregressive model. But oftentimes, to use a tool like ARIMA, you might need years of experience. Really, what we want is a tool that will allow us to hit the ground running, right, as quickly as possible. Another thing that people might want to do is anomaly detection in their time series data. But oftentimes there's challenges with anomaly detection because the first thing that you got to do is define what an anomaly is, right? So, and maybe it's a rare event and it happens once. What happens if that rare event happens a second time? Is it still an anomaly or does it become normal now? Do you have to change your definition? What's also popular these days is folks who like to do forecasting. Facebook Profit is a fantastic tool for doing forecasting by utilizing additive models. But this also makes the key assumption that historical data is useful for at least forecasting the future. Of course, there's machine learning, whether you're looking at linear models or decision trees. What you might end up with when you're trying to analyze time series data or when you're trying to build a model based upon time series data is interpretability, right? That becomes a key concern. And you can get also into unsupervised learning by doing clustering. So you have multiple time series, and you might want to group some of them together that look alike, whatever that means. And then last but not least, if you have time series data that is of different lengths, you might have some that are longer and shorter, and you want to compare them, then you can do something called dynamic time warping, where you compress and stretch that time series and so that you can compare them. And that particular method actually comes out of the University of California, Riverside, by the same group that came up with this sort of matrix profile idea. And of course, in the age of artificial intelligence, how can we not talk about deep learning, everybody's sort of favorite hammer looking for a nail to hit. And in this particular case, now you need tons of data and also compute power, probably in the form of GPUs, right? Now, the goal here isn't to point out necessarily all the pros and cons of all these methods. But the point here is that even for time series analysis, there is no silver bullet. Or to put it differently, there's no free lunch. Regardless of which method you choose, there's always compromise. Each method is good at a different thing. And really, we want you to choose or try as many of the methods as possible when analyzing your time series data. Now, having said that, I'm sure everybody's thinking, oh, Sean, another new method? This is sort of analysis paralysis. I'm getting exhausted thinking about it. And hopefully what I'm going to do today is convince you that Stumpy and the concept of something called a matrix profile isn't actually a new method. It's actually very, very old, but similar to things like deep learning, where it has become en vogue again. Thanks to better algorithms and better compute power, we're able to do something that wasn't possible before. So let's get started. Let's start with an illustrative example. So here's a simple time series that has 13 data points, okay? And if you looked at this, the first few things that you might notice about these 13 data points, n equals 13, is that it's bounded between 0 and 15. So the smallest number is 0, the largest number is 15. If I were to ask you, is there anything interesting about this data set? Are there any patterns, any anomalies? Now we can reach for one of those magic spell methods, which is to visualize our data. Now we can see, okay, some things are higher, some things are lower. But really, how might we start analyzing this simple time series? Now, before we get started, let's start with a simple definition. So a subsequence. So I'm going to say this word a lot, subsequence. And a subsequence is nothing but a part or section of the full time series. So going back to our example here, this part, these two data points here could be a subsequence as long as they're continuous. These three data points here can also be a subsequence. These 8 data points can also be a subsequence as long as it's shorter part of the full time series. It's just called a subsequence. Okay. So now that we've defined this, so then what's the goal? When we're analyzing time series data, we should think to ourselves, what is a goal, right, that we would want to extract? What information would we want to extract out of this data? And I like how the original authors of Matrix Profiles sort of define this or explain it. They say, if a behavior is conserved within your time series data, there must have been a reason why it was conserved. And then teasing out these reasons or causes is often very useful. So it's really thinking about conserved behavior. And in fact, if you think back to all of those sort of magic methods that we were discussing, all of them really depend on conserved behavior or make an assumption that behavior is conserved. That means that there's maybe some pattern in your time series. So if we can sort of unlock this, right, then we're ahead. So there's really 2 main questions that we should be asking ourselves every time we get a time series data set. The first question is, do any conserved behaviors exist in my time series data? So here, notice that I don't assume that there is conserved behavior. I ask the question, is there any? And then if there are conserved behaviors, what are those conserved behaviors or what are those patterns in your time series? And the second thing is, where are they located within that time series? So how might we answer this question?
Sean,
right? Yeah.
Is it okay to interrupt for the quick question?
Sure.
Here, the word conserved, you mean to say that, like, as I take one of those subsequences before, that same property or behavior about the whole sequence applies to the subsequence? Or, yeah, how are you using conserved here more precisely?
Yeah, let's wait until, as we develop our illustrative example, I think it will be a bit clearer.
No problem.
Perfect. I appreciate the enthusiasm, actually. So kind of as a reformed scientist, right, if I were to take an approach to analyze the time series data, I always think back to Occam's razor, right? And Occam's razor states that simpler solutions are more likely to be correct than complex ones. So essentially, you're favoring simplicity over complexity, okay? And so if I were to ask myself, okay, what is the most simple and intuitive approach that I can take to analyze this time series? Now, there are a couple of key qualities that I would want coming out of this approach. The first thing is that it needs to be easy to interpret. My biggest pet peeve, especially thinking about machine learning, right, is if you think about a confusion matrix or thinking about precision and recall, every time I have to look it up because I haven't touched it in a while. So whatever the approach is, needs to be easy to interpret. That means that it doesn't require any mental gymnastics for you to understand the results. And even if you came back months later, within a minute, you should be able to reorient yourself very quickly. So another thing is that whatever the approach is has to have minimal assumptions. And this is minimal assumptions about the practitioner or the user, right? So that means that you don't have to have expertise in order to use this method. But it's also a second thing is that it doesn't assume anything about your data. It doesn't have to be specific to a certain domain. Similarly, the approach has to not require no prior knowledge. And what I mean by this, if you think about machine learning examples, you often have to train your data on historical, train a model on historical data. And to me, that's sort of requiring prior knowledge or prior information. And whatever approach that we're taking here to analyze our data, hopefully it doesn't require sort of doing that. You can just put your data in and it gives you information back, right? And then the last maybe interesting quality to have is hopefully the approach can be parameter free. Or at worst, if you have to choose a parameter, that parameter needs to be really, really obvious, right? What it means in the grand scheme of things. So in the case of time series or looking at subsequences, one parameter, for example, is, let's say, choosing the subsequence length, okay, m. So in this particular case, let's say we choose m equals 4, right? Now, usually And this will be, I promise you, the only parameter that we're going to choose is the subsequence length. And usually this is related to the data itself. If you're collecting data at a every second interval, then maybe your subsequence length is at a minute length, right? Or at an hour, or even a week or a month. It's up to you. But at the same time, this subsequence length M shouldn't be sensitive, shouldn't be so sensitive, right? And we'll sort of explain this a little bit later too. But so let's say we choose a subsequence length M, and in this case it's 4. Then we can start thinking about how do we compare subsequences? Because we talked about earlier, hey, how do we assess conserved behavior? And really what we mean here is that given, let's say, this subsequence shown in green here, is it conserved? Or to put it differently, do we see this subsequence again? Okay, either exactly or nearly the same, right? And when I compare subsequences, I might compare this green subsequence to this blue subsequence. So if you look at these two, how might you as an audience compare them? What's perhaps some obvious ways? For myself, one sort of intuitive way, right, simple way to compare these two subsequences is to compute something called the Euclidean distance. And the Euclidean distance is the straight line distance between 2 points. So going back to basics here, what does that mean, right? I know we're using words here, but practically speaking, here's what it means. You know what? Let's not even compute Euclidean distance for subsequences of length 4. Let's go back and look at something shorter. So on the left here, we'll call this X, right? The green one we'll call X, and X has 2 data points, 0 and 1. The blue subsequence, we'll call it Y, and it has also 2 data points, Y1 and Y2. And notice that when I'm using lowercase x and y, that's just referring to the individual data points within their corresponding subsequences. Now I can plot the green one on the bottom left here, 0, 1. I can also plot the blue one in the upper right. And the definition of a Euclidean distance was simply that it's a straight line distance. So I draw a straight line, and this is our Euclidean distance, done. Right. Now let's not even give it a special name. Let's just call it h. Now we all actually know how to compute the distance between these 2 points here. Once we draw a right angle triangle, label the sides as A and B, and hopefully this will look very familiar to you. H squared is equal to A squared plus B squared. And if we take the square root of both sides, we get this Euclidean distance. In fact, this is nothing but our friend Pythagorean theorem. So hopefully everybody recognizes that, right? So there's, if you're in middle school or high school, you should probably recognize this immediately. And if we plug in our numbers for A squared and B squared, as shown below, right? So we take the first data points, x1 minus y1, we square it, and we do the same thing with x2 and y2, right? And we substitute our numbers in there, and we compute it, and we see that h is equal to root 2. So the distance between these two subsequences is root 2. They're not identical, because if they were identical, the distance between them would be 0. So this gives us a measure of how conserved, well, maybe how similar they are. So we'll talk about conservation later, right? But given any two subsequences, we have a way to measure how similar or dissimilar they are. Now we built this intuition up to subsequences of, going back to our example, length 4. You notice that our Pythagorean theorem changes a little bit. So now that we've added a third point, in both of our subsequence x3 and y3, that's now captured in the c squared term. So you subtract them and square them in a very similar fashion. Same thing with our x4 and y4 terms. That's captured in the d squared term. So as you add more and more, as you increase the length of your subsequence, you just add more and more terms in very much the same analogous way. And when you're plugging your numbers, you'll see that the distance between these two subsequences is square root of 67, right? And then more generically, for those who are mathematically inclined, this is sort of the generic formula for computing the distance between two subsequences of the same length, but that are, of length m, right? So this xk corresponds to one of these elements in your green subsequence. Yk corresponds to one of the elements in your blue subsequence. And then as you're going from k equals 1 through m, right, and subtracting and squaring them, it's just running across the subsequences. And you can compute this distance between any two pairs of subsequences. So I'm going to pause there for a second to ask if there's any questions.
Oh yeah, there was a question from Kinesh about how you would define behavior. I think you mentioned it earlier, and so yeah, curious to get your thoughts there.
Yeah, so I think what we're talking about, again, we're gonna evolve into this in a second, right? But behavior, conserved behavior is more talking about whether or not a subsequence is seen again. So if you think about time series, right, you're probably measuring some, let's say, IoT sensor, or maybe you have a temperature thermometer that you're measuring the external temperature, and things are constantly fluctuating and changing, right? But in sequential order, does a subsequence repeat itself, right? So that's what we mean by conserved behavior. Because if you think about weather itself is kind of seasonal, right? So things that we might see this year, we're probably going to see again next year and the year after that, right? So that's sort of what we're getting at as conserved behavior. And similarly with systems, you'll see potentially conserved behavior. But again, we don't assume that conserved behavior exists within our time series, because it could be completely random. What we're doing here is really asking the question, do we see sort of this repetition, right? And notice here that when we're computing these distances, we don't require that something has to be exactly a zero distance. It could be maybe close enough, right? So we're allowing some wiggle room. Were there other questions?
Yeah, an additional question that came up was before you were measuring those, or you were comparing those subsequences, and they had length 2 initially, and then later on length 4. Should we divide by the length of those sequences to try to get to a more greater understanding of what length we should be comparing for the subsequences? How do you pick the length of the subsequences?
That's a great question. So usually with the length itself, so there's two parts, right? The first part is, should you normalize, right? So and then the second part is, how do you choose the length? So in normalization, I've sort of purposely removed some of the complexity, but usually what we actually do is we z-normalize our subsequences, which then means that if there's differences in those subsequences, sort of a vertical change or an increase in trend, both of those subsequences will be brought down to the same level, and then therefore you can compare them simultaneously. But this is a matter of whether you z-normalize your Euclidean distances or you don't do any normalization at all. So Stumpy gives you both types of capabilities. Each are good at different things. If you're looking at conserved patterns, you certainly want to z-normalize. But if you're looking at something like anomalies, normalization often aren't good for that, especially for sort of spikes with your time series data. Now, the other question about how do you choose your M? Generally speaking, you want to choose an M that is large enough to sort of encompass the period of time that you're interested in, But at the same time, the way that I like to educate people is you got to think about, especially if you're in a business setting, right? Is you got to think about your business partner. How quickly can they take action? Right? Because if you choose a time period that is, seconds or minutes, right? But it still takes some hours before they can, or days to take action, right? That's probably not a useful metric. But at the same time, it requires a little bit of domain expertise on the underlying data itself. But again, with the M, as long as it's larger than the pattern that that may or may not exist, right? Then you should be fine. So M is actually not that sensitive as long as you're a little bit larger. But the point here is that, right, you want an efficient algorithm that allows you to try many different M's at a very, very low cost, right? So you can try 10 different M's simultaneously and quickly without high cost.
There was also a follow-up on this this conserved behaviors, which is how do you identify the conserved behaviors to be looking for? What's the universe of conserved behaviors that we should be looking within?
Yeah. I think that once we get to the next section, because I think that perhaps people are getting a little bit hung up on the human needing to know ahead of time. And we'll get to a point where we're saying, you don't actually have to know what behavior or what conserved behavior you're looking for, because we're going to search for everything, so to speak. I think that will help.
Cool.
Right.
Thanks.
But so far, what we've established here is, let's say you're lucky enough that somebody gave you that green subsequence, right? Somebody knew and they gave you that green subsequence, and they said, compare it to this blue one. Now you know how to compare it. But to the question about conserved behavior, what if you don't know the green subsequence or the blue subsequence? You just have time series data, and you need to sort of analyze everything. How might you do that? And that's what this following section will help us better understand. So how might we now compare this green subsequence and say, is this green subsequence now conserved across the entire time series, right? In order to do that, we have to compute pairwise Euclidean distances. So that means that, what I'll do is, for simplicity, I'll repeat the sequence underneath, and I'll put my blue subsequence down here. So and then I'll compute pairwise distances, and I'll store these distances in this distance vector, so to speak, down below. And so I'll compare green and blue. Well, they're the exact same, so the Euclidean distance between them must be 0. But then what I'll do now is I'll slide over the blue subsequence over by 1, and I'll compute the distance again. And I keep sliding it over and compute the distance, right? And essentially what I'm asking here is this green subsequence conserved somewhere along this time series? Or to put it differently, how close is this green subsequence to every subsequence within this time series? And this is captured in this sort of distance vector, or in the literature, this is called a distance profile. So just this vector here. And this can be computed in O of n by m time. Now, if we're asking about conservation, then we can ask, well, which subsequence within the time series, which blue subsequence matches or looks closest to the green one? Well, obviously, this one looks the most like the green one, right? This blue one looks the most like the green one because it's what we call the self match. And this is the trivial match. This is the no duh, right? But we're often not interested in the trivial match. So we'll typically blank that one out. And then what we do is we travel along our distance profile and we look for the next best match. And that is the next smallest number. And that happens to be this one here. This blue subsequence is the next closest match to the green one. And it has a distance of 6.9. Again, it's not 0, right? But it's also not, infinity. You can kind of see that they're close-ish, maybe, right? But this is the closest one. Nothing else is closer than this. And we can continue this process, maybe because somebody handed you the green one, this green subsequence. But what if you don't know what you're looking for in the first place? So then what you would have to do then is say, okay, well, let's shift it over. Let's shift over our green subsequence over by 1 and do the exact same thing again. So compute the distance between green and blue. Done. And we keep doing this and sliding the blue one across again. And we get another distance profile that is specific to the green one. And we're basically asking, is the green one conserved somewhere? And obviously we'll throw away the self-match and scan along a distance profile and find that, hey, there's one over here with a distance of 1.4 away. That's smaller than the first subsequence that we last looked at the last slide. 1.4 is pretty close to 0. And if you visually look at these two numbers here, right? The first numbers are the same. The second numbers, 3 and 2, are off by 1. The third numbers are the same. And the last number, 9 and 10, are very, very close. So here we're able to think a little bit more about conservation, right, of these subsequences, of this behavior. Now, we shouldn't stop there, right? So we've slid over our reference or our query subsequence, this green one, over by 1. In fact, we can just keep doing this. We can keep sliding over that green subsequence and analyzing in a sort of a brute force fashion, right? What all the distances are. And this is what you get on the left-hand side here, all of these distance profiles. And we've basically surveyed the entire time series, looking for its nearest match or its best match. In fact, we look for all distances, and then we pull out the one that's most interesting, right? Because we're interested in conservation here. And when we take these distance profiles and we stack them one on top of each other, and we sort of remove the grayed out area, this is just called a distance matrix, right? Nothing too complicated. Distance profiles stacked on top of each other is a distance matrix. And if we think about this distance matrix, it's fairly intuitive because remember, our goal here is to come up with a simple and intuitive approach that we can understand. When we look at this, we have all of the sort of useful information that we would want, right? How close is each subsequence to some other subsequence within the time series? And so have we achieved our goal? Yes, I think that this is pretty intuitive and simple. And also there's some of the key qualities. Is it interpretable? Yeah, we know how to interpret something as is close to each other or far away. We haven't assumed anything. This can be applied to any time series data. We didn't have any prior knowledge in the sense that we didn't have to train a model. And in terms of a parameter, we've only had to choose the subsequent length. So that's great. That seems almost too good to be true. And so it's like, wait, but what's the catch here, right? Because we can find what's conserved, so to speak, but we should be asking ourselves the question, is this solution scalable, right? Is this algorithms?
Can I raise another concern that I would have just from the previous slide?
Yeah.
This was before I saw your fish. So I think you've also chosen the distance metric. In terms of parameters, I agree that you've chosen the length as a parameter, so you're choosing the dimension that you're considering all this in, but you've also implicitly chosen kind of the shape of that latent geometry, or that geometry that you're considering this within, by saying that we're going to pick Euclidean distance. And I know that's reasonable and canonical, but I do think it's a choice.
I think that's a fair assessment, but in being aligned with Occam's razor and being simple, right? I support the idea of using a different metric as long as we're not adding complexity, right? Because we can make that choice at any time in the future, right? But the current choice that we're making is favoring simplicity over complexity.
Mm-hmm. Mm-hmm. I guess one could even argue that in that case, then Manhattan distance, but your point,
Absolutely.
I think, is very clear, though.
Absolutely.
Thanks.
Also, the other thing that, whenever I see giant matrices like that, I think about, and I know it's not exactly the same here, but multiple comparisons.
What do you mean by that?
Looking over large sets and kind of picking out. So how do you think about that here?
And maybe what you're touching upon is potentially the scalability of this, right? Of this approach. Is that what you're getting at?
No, I'm looking at finding spurious results and.
So what we're looking at is looking for anomalies. Because if you think about it, right, that all of these sort of small green boxes, we're choosing the closest match. But at the same time, if you have your closest match actually has a very, very large number, a very large distance from you, what it's telling you is that subsequence doesn't have anything that's close to it, right? Which is also valuable. It's like the absence of conservation, so to speak.
Cool, thanks. And then there's also a question from Timothy around is there great sensitivity in one result based on choice of distance or similarity metric?
It can be argued that there could be, but again, what we're presenting here is research results, right? I would say that the group over at the University of California, Riverside, Iman Keogh's group, they've been dealing with time series data for a very, very long time and are far smarter than I am when it comes to time series data. And they've found that typically Euclidean distance, specifically z-normalized Euclidean distance, tends to produce the best results that is generally applicable. Obviously, we're talking about no silver bullet here, right? So it's really your best bet is to try different metrics when possible. But not all metrics are amenable to fast computation, which is what we're going to touch upon in a second. Anything else?
I think we're good for now.
Great. So I know that we've sort of explained it. Hopefully everybody has developed an intuitive sense of, okay, I can find something that is close to a subsequence, right? Or find out what its nearest neighbor is. And we were asking this question like, well, is this solution scalable? So if we were to naively approach this and perform the brute force calculation to compute this full distance matrix, to do this, we can do this in Python. And so at the bottom, we have our time series, right? I've just repeated it twice like I did before. And TS are these same 13 data points that we have down here. N is our total time series length. M is the subsequence length that we desire. And to compute this distance matrix, it's actually just 6 lines of Python code, okay? And I'll step you through this. So there's actually 3 for loops that I want you to focus on. The first for loop, this for I loop, controls the green subsequence and how it traverses, right, across how it slides across your time series. The for J loop controls the blue subsequence as you're sliding that across as well. And then finally, the for K loop is for computing your Euclidean distance, okay? And that's just this K down here. And that's it. You have a triply nested for loop. And for those who are really good with computational complexity, you'll notice that this is essentially O of n squared by m, which is horrible. So most of the time when you try to compute a matrix, a distance matrix like this, for let's say 10,000 data points, your computer essentially screeches to a halt. And in fact, if you then also try to store this distance matrix in memory, this is O of n squared, which is pretty bad. And really to put it into perspective here, this is sort of a back of the envelope calculation. Imagine if you had an IoT sensor that was collecting data for 5 years, 365 days a year, 24 hours a day, 60 minutes every hour, 20 times a minute. This means that for 5 years straight, your sensor is collecting data every 3 seconds. In total, your data set would contain 52 million data points. And if you were to take this time series data and perform a brute force calculation to compute this distance matrix, it would take roughly 4.4 years to compute on a modest hardware, and about 11 petabytes of memory to store. I don't know about you, but I don't have 4.4 years to wait, right? As a data scientist, I want things to be, there's different scales. So maybe I go grab a cup of coffee and come back and have it be done. Or maybe if it's a large enough data set like this one, right? Something much, much faster. So if we ask this question, does computing this matrix, distance matrix, is this solution scalable? Sadly, it is not scalable. And it kind of explains why all of these methods that we talked about before are so popular, because we have many mathematicians and computer scientists working on these problems and really making sure that these solutions are right there for you to use, right? And that also explains why the most simple and intuitive approach nobody has really ever talked about, because it wasn't scalable. That is, until now. And otherwise it wouldn't be that interesting of a talk, right? And this goes back to these researchers at the University of California, Riverside, and University of New Mexico. Back in 2016, they came up with something called the matrix profile. So they published a series of back-to-back papers. Now they've actually published, I think, 21 papers relating to something called a matrix profile. And they define the matrix profile as a vector that stores the distance between each subsequence within a time series and its nearest neighbor. So a matrix profile is a vector that stores the distance between each subsequence within a time series and its nearest neighbor. I know I've said a lot of words there, but you actually know what this means. So what this means is that on the left-hand side, we have our distance matrix that we've seen before, and the matrix profile is nothing but pulling out all of those green boxes, which is your nearest neighbor, and storing it in a vector. And that's it. And so they were saying that you only need this, right? Most of the time, knowing the matrix profile, you can do a lot with it. And what's really nice about having a matrix profile is that it only takes O of n space. But they also showed in their paper that to compute the matrix profile, even though it's an exact solution, that means that you have to compute all of the distances and then pull out the smallest one, they could do this in O of n squared time, not O of n squared by m, right? Which is phenomenal. And with this matrix profile, then we can go back to the very beginning of our talk, which is answering the questions of, do any conserved behaviors exist in my time series data? And if so, what are they and where are they? So this was our original illustrative example of our time series. We can annotate this time series using our matrix profile. And if we look at this matrix profile, we can also plot it, right? And immediately plotting it, what we see is there's some minima here, right? And it also goes up in the middle here, right? So there's some global maximum. Now, when we're talking about conserved behavior, the first thing we want to know is what might be conserved, right? And this is, or is anything conserved? And in order to do that, what we actually do is we look for the smallest values in our matrix profile. And you notice that there's 2 values here that are very, very small. Everything else is like maybe 6 and above, right? But these 2 values here, 1.4, are quite small compared to everything else. And when we actually look at the one on the left, right, that corresponds to this subsequence, the one on the right corresponds to this subsequence. And it turns out that these 2 are pairs of each other. This is our conserved subsequences within our data. Like very quickly, by looking at the minima, we can pull out conservation. Now this may or may not be interesting, but at least by looking at the matrix profile, it tells you where you should be focusing first.
Sean.
Yep.
uh, should the lower chart be slid to the right by some number of steps? Because as you were saying, this like 1.4 corresponds to the second. So
No,
maybe
this
just
is
one
correct.
step to the right.
No, this is correct.
Then
This
why is
correct.
the first point not 0? That's, I guess, my real question.
Why is this point not 0? Is that what you're asking? Why the matrix profile here is not 0? Because this is corresponding, this is asking the question for the subsequence 0, 1, 3, 2. What is the nearest neighbor, right?
Yes, yes.
So each one here is annotating the subsequence directly above from it.
Great. Thank
right?
you. Thank you.
Great question, though. Great question. So interpreting this sometimes is a little bit challenging. So that's a great question. So in this particular case, each one of these is annotating a particular subsequence directly above it, all right? And that's why all the way at the end here, we're missing sort of 3 distances, is because we've run out of subsequences of length 4, right? So it ends at this subsequence. 2, 2, 10, 7 is the last subsequence. There's nothing else beyond that, right? So in this particular case, we've sort of looked at, we found a potential pattern that might be interesting. And that's by looking at the minima here. Now, in the sort of matrix profile of time series parlance, this is often referred to as a motif. So the sort of global minima or potential pattern is called a motif, okay? And oftentimes what you'll find is that if you have a much longer time series, you might have more minima along the way. So if you even think about a sine wave with noise, interspersed through it, right? You'll probably see that there's minima that are 0, right, along the way. Okay. Now there's another thing that that will help here, right, which is that is defined as a matrix profile index. So last we talked about the matrix profile, which is the distances, but the matrix profile index is the index location of the nearest neighbor for a given subsequence. So here we're talking that we've stated here the matrix profile tells you the distance, the Euclidean distance to your nearest neighbor, but where in the time series is it, right? Because that's the second part that we want to know is, where is it? So if you notice at the top here, I've added a 0-based index, okay, for that time series. And for the subsequence on the left, the green one, its nearest neighbor is actually at index 8, which is where the blue one is. And similarly, for the blue one, its nearest neighbor is located at index 1. Okay, and in fact, for every subsequence along this time series, it has not only a nearest neighbor, but the location of its nearest neighbor. So this is the output that you would get when you're analyzing the matrix profile. Now, just to drive home the point here, for instance, here's another subsequence. Right? Now we can look, by looking at a matrix profile and the matrix profile indices, we can then just come down and say, hey, where is its nearest neighbor? Its nearest neighbor has a Euclidean distance of 6.2 away, and it happens to be located at index 2, which is this blue one here. So this is how you read these matrix profiles and these matrix profile indices. Hopefully that is clear. Okay. There's another thing that we can do with matrix profiles, which is looking at potential anomalies, right? Or a different way to put this is, are there any subsequences that don't have a particularly good match? And to do that, we just look across our matrix profile and look for the largest values. It just happens to be this 14.1. And that's this subsequence. And what this tells us is that it's a maximum, and that this particular subsequence doesn't have a good match. So it's not at all well conserved. Now, it's not to say that if you have more data coming in that you're not going to see it again, but within this time series, nothing is a particularly good match. And what people might be interested in doing is taking this matrix profile, which again tells you the distance to your nearest neighbor, and maybe computing some statistics on it and comparing and saying, well, what is the mean? And 2 standard deviations, above the mean or below the mean, right, might give you potential anomalies. Okay, so these are the 2 ways that you can quickly leverage matrix profiles. And sometimes this is called in again matrix profile parlance. This is called a discord. So it's a potential anomaly. And so just sort of thinking about performance here, right? We talked about the brute force computation to compute all the distance in an exact fashion, takes O of n squared by m time. And then these academic researchers, actually in the first paper, they published an algorithm called STAMP, where they use fast Fourier transforms, and they actually got this time complexity down to O of n squared log n. And then in a follow-up paper, they published something called STOMP, which is just really nice sort of equation manipulation to get the time down to O of n squared. So this is on CPUs. And then they also ported it over to GPUs. So they have a GPU stomp code that also does this very, very quickly, but on many, many threads on a GPU. And they were able to analyze for a time series of 100 million data points. This is huge. This is even more than that back of the envelope calculation that we had. They were able to use their GPU stomp implementation and compute the matrix profile in just 12 days. And if you think back to that example that I had, right, to collect 100 million data points would probably take you 10 years, or at least in 5 years, right? But at twice the frequency. And being able to compute it in 12 days is actually phenomenal. But most of the time, your data set isn't that big. But the point here is that it's scalable. And if you ask the primary investigator, Eamon Keogh, shown on the right here, he says that given a matrix profile, right, most time series data mining problems are trivial or easy to solve in a few lines of code. In just a few extra lines of code. As long as you can compute that matrix profile, a lot of stuff can be done in a few extra lines of code. And he also later went on to claim that these are the best ideas in time series data mining in the last 2 decades. And in my opinion, anybody who says this has to be a real gangster. Okay, but extraordinary claims require extraordinary evidence. And that was stated by the late Carl Sagan. And that's the point of Stumpy. Our exploration into these matrix profiles and computing efficiently matrix profiles was to see whether this was completely hype or fabricated, or maybe it was real. And it turns out, in our experience, all of the things that were published about computer matrix profiles were actually correct. And that you can do this efficiently. But I will tell you that there's a lot of really nasty, hidden tricks and missing things in the publications. Not because there's any ill intent, but just the nature of publications, right? Having page limits. And so Stumpy tries to faithfully reproduce that academic work so that you don't have to, right? And what is Stumpy? So Stumpy is a powerful and scalable Python library that efficiently computes the matrix profile, and then which can be used for a variety of time series data mining tasks. We recently celebrated our 1-year anniversary, so we're pretty happy with that. Just over 49,000 downloads and installs. We have 1.4 thousand GitHub stores, so we're really thankful for all of our users for supporting us. We recently bumped up our version to version 1.5 as of September 2020, and you can conda install Stumpy using the conda forge channel, and you can also pip install it as well. And what's really, really great about Stumpy, right? As a data scientist myself, I find that if you have, you're installing software and there's so many dependencies. Well, we purposely designed Stumpy to have minimal dependencies. Stumpy only has 3 dependencies. So assuming you're using, modern Python 3.6 plus, Stumpy only depends on NumPy, SciPy, and Numba. So for most people, I'm guessing that you probably already have NumPy and SciPy installed. And for parallelization, so parallelizing Stumpy across all of the cores of your server, we use Numba. For those of you who aren't familiar, Numba allows you to write Python code, and then it JIT compiles it to highly performant code for you. And it allows you to essentially avoid the global interpreter lock within Python. Now, if you do have large amounts of data and you happen to have a Dask cluster available to you, Stumpy also plays well with Dask. So Dask is not a hard dependency, but if you do have a Dask cluster, you can hand the Dask scheduler over to Stumpy, and it will handle everything for you very, very nicely. But again, Dask is a soft dependency, not a core dependency. Now, thinking about performance, we mentioned earlier that the state of the art, right? Computing a matrix profile for 100 million data points using the GPU implementation took the authors 12 days. In our particular case, in our first venture into this, we used 256 CPUs spread across 8 servers. Spread across 32 servers, and we were able to compute the matrix profile in just under 10 days, right, on CPUs. Now, this isn't to say that CPUs are faster than GPUs. That's not the case. The point here is that using the right tools for the right job, right, using Numba, Dask, NumPy, SciPy, we actually can build very highly performant code. And in fact, we started from Python NumPy code and then converted into Numba Dask code in just 7 days and scaled up to 256 CPUs, right, which is phenomenal. Especially if you're a Python user. So don't let anybody convince you that Python is not scalable or isn't ready for production. Now, our version of these stamp and stomp functions, we actually just call it stump. It's a play on words, and I'm a sucker for play on words. The U in stump sort of pays homage to NumPy, the U in NumPy and Numba. And also because I'm based out of Ann Arbor, Michigan. Ann Arbor is often known as sort of tree town or tree city, United States. So that's a little bit of tidbit where the name Stumpy came from. And if you ever see any of our functions ending in ED, that just means that that particular function also has a Dask component to it that you can plug into Dask. Now, we also have a highly performant GPU implementation. So once you get to about, maybe 500,000 data points or more, CPU on a local machine just doesn't cut it anymore. So you'll want to move up to GPU stump instead. Okay. And so if we ask our question, what's the most simple, intuitive approach that we can take? Computed matrix profiles, I think, is a very simple, intuitive approach. And is the solution scalable? Yes. Now that we've scaled it to many, many CPUs and also to many GPUs, we can say success, right? This is a scalable solution, and this is why you've never seen this method, prior to now, right? It's because it didn't used to be scalable, but it is now. Now, from an API standpoint, how might you use Stumpy? So imagine you have a time series, in this particular case, TS, that has 10,000 data points, and you choose some subsequence like M here. To compute the matrix profile, it's fairly simple. You just import Stumpy, and you say stumpy.stump, and you pass it the time series, and you pass it your desired subsequence length. And in fact, if you have GPUs available to you, you just have to say stumpy.gpu_stump. The only difference here is 4 letters if you want to go from CPU to GPU. And for those who are concerned that, oh, well, what do I have to do to get it to GPUs? You actually don't have to do anything. If you already have a GPU machine and you're already running, PyTorch or TensorFlow or QPy, right? All you have to do is install Stumpy. And because we have Numba actually JIT compiles Python code immediately targeted for GPUs. So you don't actually have any other dependencies. And I'm sure some people are saying, can I have a GPU too? Well, it turns out you can. So you can access Google Colab. Colab is essentially sort of like Google Drives meets Jupyter Notebooks all in one. And they actually give you, I think, roughly 12 hours of GPU time. So if you go to the link down here, tiny.cc, Stumpy_Colab, we have a notebook there that you can sort of look at how you might use the GPUs and run Stumpy on them. In addition to the GPU stump, we've sort of talked about analyzing and getting the matrix profiles and looking at conserved behaviors for single dimensional time series. So let's say instead of one IoT sensor, you have many IoT sensors, right, that are measuring different things in a room that you're in. So that's called M-stump. M standing for multi-dimensional. Okay. We also have something called Scrump, which gives you approximate matrix profiles. So you can spend 1% of your compute resources or 1% of your time to compute an approximate matrix profile, just to give you an idea of whether you want to spend the full time computing it. And then last but not least, for those of you who have streaming data, Stumpy with an I, the I stands for incremental, is for streaming data. So if you have a new data point coming in, you want to forget about your oldest data point and sort of have a sliding window, you can use Stumpy as well for that. And so making the case here, I think a lot of people are thinking as well, why should I use Stumpy? Because there are perhaps other implementations of matrix profiles out there, right? But I will say that you should use Stumpy because it's highly user-friendly. It was developed with data scientists in mind, right? If you can't install Stumpy within, a minute or 30 seconds, we've sort of failed you. We want you to be up and running quickly and be able to analyze all of your data in a very simple and user-friendly interface. Also, it's interpretable. We're just using Euclidean distances, or as we kind of pointed out earlier, just Pythagorean theorem. It's highly interpretable. It's very easy to consume here, even months later if you have to come back to it. But also, this is not a toy project. This is not an academic project. Stumpy is fast and scalable. We've scaled out to multiple CPUs and also multiple GPUs. In fact, we've scaled out to a DGX2 cluster without changing any of our code, which is 16 high-end GPUs. But the thing that I'm most proud of in Stumpy is its reliability. So from day one, when we released Stumpy, we had 100% code coverage. Even till today, we have 100% code coverage in terms of unit testing. That means every function in Stumpy is tested. And in fact, not only do we test our code, and it's not just simply, here's known inputs and we expect this output, we also implement naive brute force implementations of these same algorithms to compare against, right? So we have all of your bases covered. And then last but not least, matrix profiles is very, very complementary. So you can sort of mix and match these methods with your favorite methodology, at least giving you insight. And it kind of takes us towards like when you should use Stumpy. You should use Stumpy with all these other methods, right? Because all of these other methods, again, assume some sort of conserved behavior or makes the assumption that some pattern is repeating. And by using Stumpy, you can help improve your intuition about your time series data set and at least tell you where you should start looking in your time series first. But again, there's no silver bullet here, right? You should really be trying everything, right? And trying many different subsequence length, so to speak. And before we get to our live demo, I wanted to sort of quote the original author here, right? Which is, you can really do a lot in time series analytics by reasoning about conserved behavior or roughly conserved behavior, right, in your time series. And the low values of your matrix profile are actually the most conserved behaviors. You're not going to see anything else. A lot of these other methods, even machine learning, gives you false positive. But because Stumpy is computing all of these distances, it is exact, right? So with that, I'll open up to some questions before I flip over real quick to some live demos.
So you managed to nail a lot of the questions just in line. One question, which I think speaks to a bigger question, the question was basically like, how would you use the matrix profile for forecasting? Are there built-in forecasting tools that use the matrix profile in Stumpy? But I think that really speaks to the larger question of, you showed us that grid of 8 things, right? Of great, like 8 things you want to do with time series. How do you know how to take the matrix profile and put it into the machine and turn the crank to do those things with the matrix profile?
Yeah, I think that's a good question. In one of the tutorials I'm going to just highlight, we'll touch briefly upon forecasting. I think that matrix profiles aren't the perfect thing for forecasting, but hopefully it will give you a flavor of what's potentially possible. I'll leave it at that, right? And then in terms of how you might use it, for me personally, whenever now I have any time series data, the first thing I do is I don't even waste time thinking, should I compute the matrix profile? I just do it, right? Because it almost costs me nothing. And I think that's the key thing here, right? Like visualizing your data, like pulling it up and plotting it, doesn't really cost you anything. Or computing global statistics, right? Using pandas or something, right? You can get that almost immediately. I almost put matrix profiles in that same vein now. Assuming that your data set isn't large, right? And then what it tells you is where you should start looking first. And so you might see that there are subsequences that might be conserved, and those can inform, for instance, how you do your feature engineering when you're thinking about machine learning, right? You can do a one-hot encoding and say, hey, I know that this thing is conserved. I'm going to add this as a feature column. And in fact, I can use these matrix profile indices to also indicate how far away is your nearest neighbor, right? That's one thing that people don't think about, is that the matrix profile index tells you not only absolutely, right, where your nearest neighbor is, but also relatively. Is it 50 elements away? Is it 100 elements away? Because if there's periodicity in your data, maybe it's like, weekly cadence that something reoccurs, you will actually capture that. And you can ask that question about all the subsequences along the way. Is there a repetition, or is your nearest neighbor some fixed distance away, right? And in terms of clustering, there's something called matrix profile distance, or MP-dist, which is a future paper that the research group published that allows you to start thinking about clustering time series as well. So I'm going to hop into the live, a couple of things, but I'll hop into live demo in a second. So this is that Google Colab notebook that I was talking about. This is that tiny dots. Yep.
Before we jump into the live, I just want to say, like, we're at 1 hour, and so for those of you that were joining us from Stitch Fix and may have some meetings afterwards, I just want to say thanks for joining and viewing, and we're going to carry on here for a few minutes to do the live stuff. But once again, thanks, and yeah.
Great, and thank you so much for everybody else's time too. Luckily, we're recorded, so people who missed this part, you can check it out. But again, here's our Google Colab notebook. It'll teach you how to spin up and turn on the GPUs on Google Colab, and also how to install Stumpy on there and then execute it. But really what I want to demonstrate here is this particular example here. And if you recall earlier, I asked you to maybe keep one of the time series in mind. And that's this time series up here. If I were to ask you those two questions, right? The first question is, are there any conserved behaviors, or are there any subsequences that are repeating itself? Can you spot it, right? And if so, where is it? And not to belabor the point, right? Even if I showed you the subsequence, that's this green one over here, right? Even if I showed it to you and I asked you, where is it along this time series, it's really hard to spot. And it turns out that it's all the way over here, right? But the good thing about Stumpy is that it actually gives this to you. So you see that these two time series are overlapping, right? So I've blown it up, I've zoomed in here on it, right? And for all intents and purposes, you can see that they're pretty close match. In fact, this is that z-normalized Euclidean distance. They're about a 5.5 away. They're not an exact match, right? Because if they were exactly the same, they'd have a distance of 0. But you would argue that these are pretty close. But with matrix profiles and with Stumpy, you can actually compute all of these nearest neighbors. And when I press play here, you'll see that I'm basically just sort of sliding this green box across, this green subsequence across, and Stumpy has found all of its nearest neighbors. And notice that its nearest neighbor doesn't have to necessarily occur afterwards, right, to the right. It can also occur in history as well. So your nearest neighbor can be behind you, to the left of you, or to the right of you. So thinking back to the machine learning feature engineering example there, right, is you can leverage this matrix profile to tell you not only how close you are to your nearest neighbor, but is it on your left? Is your nearest neighbor on your left, or your nearest neighbor is on the right? Or you can actually have information for both of those, your nearest neighbor on the left and the right. And so this is a particular, to me, a very interesting example, right? But again, usually you don't know what that green subsequence is, so you sort of scan everything, and that's what the matrix profile gives you. I really strongly urge everybody to check out the Stumpy documentation. There are some great tutorials, API, instructions about how to install, but just to highlight a couple of them, one of them is related to time series chains. So this is touching upon what Brian was asking about in terms of forecasting. So if you can imagine that you have maybe a conserved pattern, right? So time series or subsequences that are somewhat conserved. And there could be different ways that subsequence can be conserved, over time. They can be sort of, if you think about these data points here, these dots here as that, these time series subsequences, you can have subsequences that are clustered together, but you can also have subsequences that evolve over time in a monotonic fashion. Maybe there's an increase in trend, so to speak, right? And this is where sort of hand-wavingly forecasting might come into play if you have this type of behavior. And here's the example that comes from the original papers. What you're seeing here is web queries. So people who are searching for the keyword Kohl's, I think on Google, so Kohl's like the shopping store. And you'll notice that from 2004 into 2014, 10 years worth, there's like this hump that happens to occur near the end of the year, right? And it's increasing over time. So there's a trend that increases over time. But another thing that so can anybody guess, maybe, either Brian or Zach, like what do you think that hump represents? Why are people searching for Kohl's?
Is that the holiday season?
Yeah, exactly, right? And in fact, when you actually analyze, so you're visualizing it, right? So you can see that something's there. You can actually compute the matrix profile, and you can pull out these conserved subsequences. And so that's what you're seeing up here, right? So you're pulling out these subsequences, and this is what you're seeing here. So over time, right, it increases. But what you'll also notice is that these subsequences aren't identical, right? But this idea of time series chains actually shows you that these are somewhat similar. It's nearest neighbor. These are each other's nearest neighbors. But what you'll notice that over time, as you increase this, there's sort of this two humps, this bimodal thing happening, right?
Thanksgiving and Christmas.
Exactly. So the first hump is Thanksgiving. And the second one is the Christmas holiday season. And what's really interesting here is that you'll notice that this first peak starts to increase higher and higher and higher. And it just so happens that this peak starts getting higher in around 2007, 2008 time. Any ideas why that might be?
Is that when Black Friday started becoming more of like a big thing?
It's actually when Cyber Monday became a big thing.
Oh,
right?
duh, because this is online. Okay.
Exactly, right? So this is, but you compute your matrix profile and it gives you this information, right? So this sort of comes for free. So it gives you an idea of sort of forecasting. But if you look at this, if you're able to extract these sort of subsequences out, you can then start thinking about forecasting out what is the next year's hump going to look like, right? How's that first peak changing year over year over year, and maybe forecast out sort of that way, right? So that's one view of forecasting. But there's also another idea of something called semantic segmentation, which is this is some data set looking at blood pressure. So in the first, you can kind of see that there's sort of two regimes here. There's one, some group on the left, and then eventually something happens, and then there's a change, right? That's shown where that gray bar is. And what's really happening is that there's a human that is lying flat on the table. That's the data on the left, and the blood pressure is pretty constant and normal. And all of a sudden, they tilted this person's table or this bed upwards and jolted them, and their blood pressure changed, right? And this is where that change point is. So if you think about change point detection, this is kind of similar to that. And so how do you systematically or algorithmically or computationally identify these change points? And the idea behind this is that if I zoom in on that gray area, this is sort of what you see, right? So this dotted line is where that gray, that sort of, that change point is. And what you're going to see is that to the left of the change point, you have a repeating pattern, right? And the idea is that if it's a repeating pattern, your nearest neighbors will stay sort of on that side, right? So these arrows point to where your nearest neighbor is. And notice that these arrows pointing to this nearest neighbor never cross this boundary, this dotted line. And similarly, once the bed was tilted vertically, then we get a change in the blood pressure. But notice that also the nearest neighbors that were identified to the right of this point in time also do not cross that dotted line, right? So looking at overhead crossings of where your nearest neighbor is, you can sort of identify regions where there's very low number of crossings, and that's how you identify these. That's how you segment your data. And then I'll touch upon one last one, which is looking at streaming data. So this is a time series. This is the same time series as a demo. And when I press play here, it's basically, and what's down below is our matrix profile for this particular data. And when I press play, it's almost going to mimic as if we're ingesting a new data point. And you'll notice how the matrix profile down below will evolve and update itself because it's finding new things that is closer to it that was never seen before. So you have streaming data. Stumpy has this particular capability. I know we're pretty sharp on time, so I want to just wrap up this particular part of the talk. So I've talked about many different things. There are a lot of things that you can do. You can look for motifs in Discord. You can do this multidimensional analysis, which I didn't really touch upon. Time series change was the forecasting stuff. Semantic segmentation for looking at change points or regimes. Machine learning features, leveraging, using that matrix profile and the indices as machine learning features. There's things called like shapelets and snippets, and many things more. But really the final call to action is contribute to Stumpy, especially if you're a minority in technology and tech. We'd love for you to contribute. We'll mentor you, we'll collaborate with you, however you want to interact. Also communicate with us. Tell us how you're using Stumpy, and also tell your friends and your colleagues about Stumpy. And last but not least, please consume. And with that, I really thank you so much, again, to Stitch Fix, to Brian and Zach for help coordinating. And I open up to any further questions. I'm leaving links on the left-hand side. Really appreciate your time.
Thank you so much, Sean. Super interesting. I have a lot of personal overlapping interests with some of these things. So I know at least personally, there's so many rabbit holes that I want to explore. One of those last things you showed, I was wondering more about kind of the clustering of the points in the Takens embedding of just instead of saying what's the closest neighbor, but just kind of what is the graph structure there. That's something that I'm very interested in personally. So yeah, there's so much interesting stuff. Really appreciate this. So.
And if anybody has any further questions, if you're shy, we like to be pretty transparent with the Stumpy project. So go on our GitHub issues and post questions, even if it's about your data and how you should be using it. Happy to converse, happy to have the discussion.